Okay, today in honors chemistry, we're going to start chapter 11, stoichiometry, which simply are calculations involving balanced equations. So this is one of my favorite topics. So balanced equations, so let's revisit them for a second. So keep in mind that the coefficients will represent the moles of reactants and products, but it also relates to the number of particles. And we talked about this in the last chapter. 1 mole of anything would contain Avogadro's number, or 6.02 times 10 to the 23rd particles. If the reactants and products are in their gas state at STP, we also know the volume. So 1 mole would occupy 22.4 liters. Now, mass and atoms are conserved in every chemical reaction. That's the law of conservation of mass. So if you have this balanced equation, so you have 1 mole of N2 reacts with 3 moles of H2 to produce 2 moles of NH3, we can check to make sure its mass balances and then go from there. So mass per mole, so you have N2, each N is 14, so that gives you 28 grams. H2 is 2.0, and you have 3 moles, that gives you 6 grams. So when you add up your reactants, 28 plus 6 is 34, so you have 34 grams of reactants, and you should have 34 grams of product. So NH3, nitrogen is 14, your 3 hydrogens are 3, so that gives you 17 grams times 2 is 34. So sure enough, you have 34 grams of reactants, so you should have 34 grams of your products. Okay, so you're going to interpret the equation below for the following quantities. So you have 2H2S plus 3O2 yields 2SO2 and 2 water. You're going to do it for number of moles and show that it obeys the law of conservation of mass. So if you want to put it on pause for a second and take care of that. Alrighty, so you should have said something like 2 moles of H2S reacts with 3 moles of O2 to produce 2 moles of SO2 and 2 moles of water. And then for your balanced equation, H2S has a mass of 34.1, and you have 2 moles, so 34.1 times 2 is 68.2. O2 is 16 is 32. 32 times 3 is 96. Okay, so when you add those up, you get 164.2. So now your products, SO2, sulfur is 32.1, 2 oxygens are 32. So when you add that up, that's 64.1 times 2, plus water is 18 times 2. So you have 128.2 for your 2 moles of SO2 and 36 for your grams of water. And so your products add up to be 164.2. So your reactants mass should equal your products mass. Now, when we work with stoichiometric calculations, we involve something called mole ratios. So for the following equation, we're going to list all of our possible mole ratios. So I'm going to start with 2H2, so I'm going to say for every 2 moles H2, you have 1 mole O2, 2 moles H2 for every 2 moles water. Now I'm going to go to O2. So for every 1 mole O2, you have 2 moles H2. And for every 1 mole O2, you have 2 moles water. Now I'm going to move on to water. For every 2 moles water, you have 2 moles H2. And last but not least, for every 2 moles water, you have 1 mole O2. Okay? So these are all the possible mole ratios you could come out of this equation. Now listen, when we're working problems, you're only going to be working with two substances out of an equation. The one you start with and the one you're going to go to. You'll never use this many for a problem. Okay, to work stoichiometric problems, number one, you have to have a balanced equation, so if you're asked to balance it, make sure you do so. If I've already given it to you with coefficients in, then it should be balanced correctly. You'll determine the starting substance, that's from the data given, so that's from your sentence that you're reading. You'll convert starting substances to mole if it's not already done so. Then you'll use your mole ratio. and make sure your units cancel, and then complete the problems to the units asked for. Okay, so we're going to start out simple. So we're going to start out with how many moles of water can be produced from 3.5 moles of magnesium hydroxide. So I think the best thing to do is take and write this above the appropriate. So you have 3.5 moles magnesium hydroxide, and we want to know moles water. So even though there are 4 substances, we're only involving this and this for this particular problem. So you write down the thing with the number first. So you say 3.5 moles MgOH2 times division bar. You want to get rid of moles MgOH2, so you go to your balanced equation to moles water on top. Now this is your mole-mole ratio, so you go to your balanced equation. If there's not a number, it's 1. So for every 1 mole MgOH2, you have 2 moles water. Okay, your moles MgOH2 cancel. You're going to be left with mole water, which is what it asked for. You're going to multiply across the top and divide by the bottom. So 3.5 times 2, and we want this in 2 sig figs, you're going to say 7.0. So that just simply says if you have 3.5 moles of magnesium hydroxide, if all goes well, you should get 7.0 moles of water. Okay. The next one, how many moles of ammonia can be produced from 8 moles of hydrogen reacting with nitrogen? So in this one, I did not give you a balanced equation. So if you want to put the video on pause for a second and write a balanced equation. Okay, so you have H2 and N2 produce ammonia, which is NH3. We need to balance it, so we're going to put a 2 here. That gives us 6 hydrogens, so we're going to put a 3 here, and we have 2 nitrogens. Okay, so it's how many moles of ammonia, so this is our question mark mole, can be made from 8 moles of hydrogen. So you have 8.00 moles hydrogen times, for every 3 moles hydrogen, you produce 2 moles NH3, so this is your mole-mole ratio step. Okay. Mole H2 canceled, you're left with mole NH3, which is where you want to go. Multiply across the top, 8 times 2 is 16. Divide by 3. We're going to want our answer in 3 sig figs, should be 5.33 moles. So if you have 8 moles of hydrogen, you should be able to produce 5.33 moles NH3. Okay, so let's try the next 2. So calculate the number of moles of potassium dichromate. So this is potassium dichromate. So this is question mark mole. Will react with 2 moles potassium iodide. So this is saying if you only have 2 moles potassium iodide, how many moles of this do you need? So you're going to say 2.0 mole Ki times, for every 6 mole Ki, you have 1 mole K2Cr2O7. 2 divided by 6.33. Okay, so if you only have 2 moles Ki, then you're only going to need 0.33 moles K2Cr2O7 to react with it. Okay, next one. Now, instead we're using 2 moles Ki. We still have 2 moles Ki, but we want to know moles of iodine. So this is our question mark mole. Okay, so we're not using this. So we're going to say 2 moles Ki times division bar. Go to your balanced equation. For every 6 moles Ki, you have 3 moles iodine. So 2 times 3 is 6, divided by 6 is 1. Okay, so this is saying instead of having 6 moles Ki, if you had 2 moles Ki, then you would expect that you're only going to make 1 mole of I2. We should be canceling out units, and I've not been doing so. Okay, sometimes in these calculations, it's not always moles. You're going to start with moles and go to grams, or you're going to start with grams and go to grams, or whatever. So it says, what mass of hydrogen can be produced by reacting 6 moles of aluminum with hydrochloric acid? So once again, we need to write a balanced equation. So we have aluminum and HCl. It's going to be single displacement. So we're going to get AlCl3 and hydrogen gas. We've got a balance, so we're going to put a 2 here. That gives us 6 chlorine, so we're going to put a 6 here. That means we're going to put a 3 here and a 2 here. Okay, so we have 6 moles of aluminum. So always right above the one, how much you have and its unit, and you want mass hydrogen. You want grams hydrogen, okay? Okay, so you're beginning things in moles, so we write down 6 moles Al times division bar. You want to get rid of mole Al, so you're going to put it on the bottom. And we can go from mole Al to mole H2. So if you're in your balanced equation, you see that you have 2 moles Al for every 3 moles H2. Mole Al cancels. However, we don't want mole H2, we want grams, so we're going to say times division bar. When you look up mass from the table, it's per 1 mole, so you say in 1 mole H2, look up its mass, 2.0 grams H2. Now your mole H2 cancels. So we're going to multiply across the top. So we're going to take 6 times 3 times 2, and then divide that by 2, 18 grams. Okay, so if you have 6 moles of aluminum, you would expect that you're going to be able to produce 18 grams hydrogen. Okay. Next one, what mass of carbon dioxide is produced from the complete combustion of C5H12? So you've got to write a balanced equation, so put this on pause for a second and write one. Okay, so we're going to put a 5 here. We're going to put a 6 here. Okay, so now we have 5 times 2 is 10 plus 6 is 16. I think that's right. So you have 8. So to balance, you should have, yep, okay. So it says what mass of carbon dioxide, so you want this question mark, grams, can be produced by the complete combustion of 100 grams of this. Okay, so now the difference is your beginning thing is not in moles, it's in grams. So we just have one more step. It's not a big deal. So you have 100 grams C5H12 times division bar. You want to get rid of grams, so you're going to say grams C5H12 on the bottom and 1 mole. So remember, anytime you're finding mass, you go to the table and look up its mass. So 5 carbons is 5 times 12 is 60, plus 12 more is 72 grams. Now we can do our mole-mole ratio. So now you go to your balanced equation for every 1 mole C5H12, you have 5 moles CO2. But we don't want mole, we want grams, so we're going to say times. In every 1 mole on the bottom, CO2, there are 44 grams when you look CO2's mass up from the table. Gram C5H12 will cancel, mole C5H12 will cancel, mole CO2 will cancel. So you're going to multiply across the top and then divide by on the bottom. So I have to say 100 times 5 times 44 divide by 72. We want 3 sig figs, so we should expect to produce 306 grams CO2. Okay? Okay, next one. How many grams of nitric acid are required to produce 8.75 grams dinitrogen monoxide? So you produced 8.75 grams of this, and you want to know how many grams of this you needed to do so. So you say 8.75 grams N2O times, we want to get rid of grams N2O, we put it on the bottom, and that's going to be in 1 mole N2O times, go to your balanced equation for every 1 mole N2O, you had 10 moles nitric acid, but we don't want mole, we want grams, so we're going to say in every 1 mole nitric acid, there are grams. So we're going to look these two numbers up on the table. So N2O, 14 and 14 is 28, plus 16. There are 44 grams N2O in 1 mole, and then 48 for your 3 oxygens, plus 14 plus 1. I think that's 63. Better put that back in. So we're going to multiply across the top 8.75 times 10 times 63, divide by 44. We're going to have this answer in 3 sig figs, so we're going to say 125 grams of nitric acid was needed. Okay. Okay, last one. So you're going to have to write a balanced equation, so put this on pause and see if you can do this one by yourself. Okay. Silver nitrate is AgNO3 with sodium chloride. Double displacement, so Na is going to go with NO3, and Ag is going to go with Cl. Don't have to do anything to balance. We have 17 grams of this. We don't know how many grams of this will be produced. So you're going to say 17 grams AgNO3 times, you got to get it to moles, so you say for grams of AgNO3 in 1 mole. So for some odd reason, this number is in my head, 169.9 times. Now use your mole-mole ratio. So every one of your problems in stoichiometry will have a mole-mole ratio. So you have 1 mole AgNO3 for every 1 mole AgCl times, if you have 1 mole AgCl, we're going to look up its mass on the table. So silver is 107.9 plus 35.5 for chlorine, 143.4. So we're going to multiply that times 17 and divide that by 169.9. That's going to give you 14.3 grams silver chloride. Okay? Okay, so that's it for your first section. And so then in our next lesson, we'll talk about other things like Avogadro's number or moles. Thank you.